Yes, we can start. Welcome to the first theory launch talk of this semester. We have Divyarthi Mohan from Tel Aviv University to talk about simplicity and optimality in multi-item auctions. Yeah, go ahead.
Thank you. Thanks for inviting me to the theory lunch. Today I'll be talking about my work in simplicity and optimality in mechanism design for multi-item auctions. And feel free to stop and ask me any questions throughout the talk. If anything comes up, even clarifying questions. I'm happy to make it as interactive as possible. This is joint work with Pravesh Kotari, Adil Schautzman, Sahil Singla, and Matt Weinberg. So let me start with the high level background or overview, motivation for mechanism design. So obviously algorithms are everywhere and they have undoubtedly changed our world. Algorithms find the best possible routes to our destination. They match available drivers to passengers, and they even operate self-driving cars around like a busy city. In many of these settings, algorithms are not just finding the best possible solution efficiently, they do so while interacting with strategic or autonomous individuals who have their own interests, so they might manipulate or interfere with the algorithm. So unlike traditional settings where we are given an input and the algorithm finds the best solution or the desired output while efficiently using resources such as computation or memory, we consider settings where there are strategic agents at play. So the strategic agents provide the input to the algorithm, and moreover, they have a stake in this process. So depending on the output, they get their own rewards or payoffs. So they might manipulate the algorithm to output a less desirable solution, even if that's not what the algorithm designer wanted, just so that they can get better rewards or payoffs. Okay. Let me try to illustrate this with a very simple example. We have a seller with a single item to sell, a soccer ball, and he faces a single buyer. And the objective of the seller is to maximize revenue. That is, he doesn't have any intrinsic value for the item. All he wants to do is to sell it and make as much money possible. Okay. So purely as an algorithmic problem, this is extremely trivial, because if you know how much the buyer is willing to pay, you would just sell it at that price, right? So here the input to the algorithm is just like her max value, and the output is going to be like, oh, sell it at max value. That's it. But clearly, a strategic buyer has an incentive to lie here and say that her value is zero. Like she values the soccer ball at most $0. Now what do we do? So this is why it's important to design algorithms that are robust to strategic behavior, and we call such algorithms mechanisms. Okay, and the field of algorithmic mechanism design exactly tackles this. It takes tools from game theory and algorithms to design mechanisms or algorithms that are robust to strategic behavior while giving good performance guarantees. Okay. And more broadly, algorithmic game theory as a field studies how different systems or algorithms performs in various strategic environments. And in this talk, I'm going to focus on my work on designing mechanisms, and in particular for revenue maximization in multi-item auctions. Okay, and I will just jump right in and tell you our main result, but I'll give you more context soon. I'll explain what these mean and why we care about this result soon. Okay. So we consider a revenue maximizing seller with n items and a single unit demand buyer with independent values for each of the item. So yeah, again, I will explain what these terms mean. So don't worry if you don't get them right now. But this is our setting. We have a seller with n items and a single buyer whose unit demand and has independent values for the items. And we show that here we can find a 1 minus epsilon approximation to the optimal revenue in quasi-polynomial time in n. Okay, so we can get almost optimal revenue in time n to the log n. Okay, so yeah, so revenue maximization is a very, very common goal in many different settings with various practical applications. But I want to talk about this very simple example we just saw a couple of slides ago. So we have a seller with a single item and a single buyer, right? So we saw that traditional algorithms are extremely manipulable because the buyer has an incentive to lie about the value. So to formally study this model, like what we do is, one way to study it is to model the buyer's value as being drawn randomly from a known distribution F. That is, think of it as us seeing a random buyer from this population F. So a random CMU student, let's say. And the seller knows how this population in general values the item. Like he knows, sorry, what happened? Yeah. So he knows how CMU students generally value a soccer ball, but does not know the exact value of this, like this particular buyer, like the random buyer he faces. Okay, so the value is still private, but like we know the distribution from which the value is drawn. So now the question is, can we have mechanisms that incentivize the buyer to report her value truthfully, that she does not have any incentive to lie about her value? And we call such mechanisms truthful mechanisms. Okay, and our goal is to find the optimal truthful mechanism. Like, what is the optimal mechanism that can be implemented truthfully? Okay. So more formally, we are given as input a single, like a distribution F, and we want to output a truthful mechanism M. So again, by mechanism here, what I mean is that given a value of the buyer, we can map it, the mechanism maps it to an allocation and price. So an allocation can be like whether you get the item or not, or like a randomized lottery of like with what probability you get the item. So it's just like you map V to an allocation and price pair. And the utility of a buyer for a given allocation and price is just her value from the allocation, like her expected value from this lottery minus the price she has to pay. Okay. And when we say a truthful mechanism, we mean that the buyer's utility or like payoff from reporting her true value V and getting the corresponding allocation and price is better than reporting any other value V prime. Okay. And our objective is to maximize revenue, that is the expected price paid by the buyer. Cool. So this is a very, very fundamental problem in economics. And in the 80s, Meyerson solved this very elegantly with a very simple mechanism, and he even won the Nobel Prize in economics for this. So he showed that all you have to do is to post a single take it or leave it price P star to get the optimal revenue for the setting. So the buyer either takes the item and pays price P star, or she gets nothing and pays nothing. So it's a simple take it or leave it price P star. So note that when you have mechanisms with like such a fixed price mechanisms, like if you want to sell the item at price P, or like you give nothing, the buyer only buys the item if her value is greater than P, right? Because her utility is V minus P. So she will only take this option if her value is greater than P. So the revenue from such a mechanism is exactly P times the probability of selling, which is P times the probability that V is greater than P. Okay. And P star is exactly the price that maximizes this expected revenue. And Meyerson showed that this is the only thing you need to do for the setting. Like you don't need any sort of randomized lotteries, nothing. Like just simply posting a single deterministic option is enough, and it gets the optimal revenue for the single item case. Okay. But we are interested in selling multiple items, right? We are studying multi-item auctions. So what happens when we just have two items to sell? So here, unfortunately, unlike the single item case, optimal mechanisms can be randomized and can even have uncountably infinite many options. So Daskalakis et al. Have this result that shows that even when the values of each of these two items is drawn independently, you need randomization to get the optimal revenue, and you might have to show uncountably infinite many options. You might have to like output uncountably infinite many options, like the mechanism outputs uncountable. Okay. So here, sorry, just a quick note about like independent values. So here, by independent values, I just mean that the buyer's value for the soccer ball is drawn independently of her value for like the baseball. And in this case, they study the setting where the value for both the items is just like the sum of the values. Okay. So why am I talking about independent values? Like, why am I suddenly like talking about her values are drawn independently? It's because in the correlated setting, things get even more crazy. Hart and Nissan showed that here, not only does the optimal mechanism have infinite many options and get infinite revenue, any simple mechanism, any finite mechanism only gets finite revenue. So there is this infinite gap between what the optimal can do and what any simple mechanism can achieve. So we really can't say much in the correlated setting. Okay, so that's why it's like important to understand the independent case. And like in this whole talk, we are only going to be talking about like independent item values. Okay, so yeah, so the question is, when in the two item case, when the value of the items are drawn independently, can we find a simple mechanism that gets good revenue? Okay, or like more generally in the case of selling n items, when the buyer's values are drawn independently for each of the items, can we find a simple mechanism that gets good revenue? And this is exactly the setting that our work considers, except I still need to explain to you one more term, like which is unit demand. Okay. So recall that so far I've just been saying that the buyer's value for a single item is drawn independently of other items, but I haven't told you how a buyer values different sets of items, like subsets of items. And many different valuations have been studied in the past in the literature, out of which I would say unit demand and additive are two of the more popular ones. So in a unit demand buyer only cares about one item. So even if you give her a set of items, it's as if you just gave her the best item in the set. So her value for a set of items is just the max value of the single items in the set. Okay. So yeah, so if you give her like all three items, it's her value for this set is only the max of like the individual values in the set. Okay. The additive buyer, on the other hand, likes however many items you give her, and her value for a set of items is just the sum of the values of the items in the set. Okay, her values are just additive over the items in the set. Okay, and in this talk, I'm going to be focusing mostly on the unit demand case. I also have some results in the additive setting. It's like very well studied, but I won't get into them in much detail. So we will focus mostly on the unit demand setting. Okay, so yeah, so this is our setting. Now I think like.
So I had a question.
Yeah.
Do the Daskalakis and company lower bounds also hold for this sort of single item unit demand case, or because you said the please.
Yeah, it does. Yeah. Okay. So they do like, I think, okay, yeah, the particular result I told you was done for like additive, but like it does go over for like unit demand.
Okay, cool.
Yeah.
Thank you.
Good. Thank you. Right. Yeah. So this is again our setting. We have n items and a single buyer, a unit demand buyer with independent values for each of the items. And we want to ask if we can find simple mechanisms that get good revenue. Okay. Let me know if you have any other questions about the setting before I get into some more detail.
I have a related question. So
okay.
Does the fact that if I gave you just a finite support distribution, does that help?
A good question. We are going to see that it's Not really. We will see that very soon. I want to get to that. Like, yeah, very good question. So yeah. Okay. So yeah, so can we find simple mechanisms? And we study simplicity formally through the lens of computation. Okay. So the formal computational problem that we are interested in is that we're given as input n independent distributions, F1 through Fn, and we want to output a truthful mechanism, and the objective is to maximize revenue. So the question is, can we do this in a computationally efficient way? Can we find the optimal mechanism in polynomial time in n? Okay. So let's try to do that. Like as Ravi suggested, like let's take a simple instance where you only have finite support here. So each of the items only take either value 1 or 2 uniformly at random. Let's try to solve this like with a direct approach. Okay. I'm not claiming that this cannot be solved in polynomial time, but yeah, let's try a direct approach with like a naive linear program. You
Sorry,
can solve, yeah.
Is there even an existence result, sort of like? So somehow, you know, you're already assuming some finiteness when you're trying to do this kind of thing, are you? Or are you writing like an infinite LP?
Yeah. So in this instance, I'm just writing for simplicity. I'm writing a finiteness here. So
right.
Yes, correct. So what happens in infinite case is going to be an issue, and that's actually why in the continuum, like usually you don't have anything that has finitely many options. That's like very so let me put this way. So in the single item case, it does not matter what your distribution is, right? You can have a continuum, but you just need one option to like do it. But when you go even to two items, the continuum really makes things very weird. Like you can't get the optimal like by like doing like finite many options. You need this uncountably many options. So that's why like we are trying to find simple mechanisms that still like get like very good revenue, but we know that we can't do optimal, but like and I'll explain even more formally why we can't do optimal and everything.
I see, but this is just a relaxation of the problem that you're trying to solve.
Yeah, so right now I'm like saying that forget about continuum, forget about infinite many things. I am assuming something like I'm saying like let's just look at a finite case where I can actually write down the LP. I'm not writing an infinite LP. This is an actual way to solve it. I can directly solve this and find the exact optimal here actually. Yeah. So there definitely exists a solution in this setting, right? In the instance that I'm solving, the existence happens. Like I'm going to show you that this linear program finds the optimal revenue. But we will see, spoiler alert, that it's not going to be, at least it's not going to be like efficient. This one.
Sounds great. Please go on. Yeah.
Yeah. Yeah. No worries. Yeah. Continue asking me questions. Like this is good. Yeah. So we are gonna like solve this instance directly with this LP. Here, what we have is that we have variables for each item allocation for every profile of the buyer's type. So here, the buyer's value is going to be like there are 2 to the n many different types of buyers. And for each of the buyer types, I'm going to have item allocation variables and price variables. Okay, and we want to maximize the expected price paid by the buyer. And we will solve this for under certain constraints. So the first one is just a unit demand constraint. Basically, it says that the item allocations just have to be a lottery on which item I'm going to set. So the probabilities add up to 1. Okay. And the second one is like the important, like the truthfulness constraint. The utility from like the buyer, the utility from the buyer for the buyer for reporting her true value and getting the corresponding allocation and price is going to be higher than reporting any other value V prime. Okay. And the third is this special truthfulness constraint called like individual rational constraints. which just says that your utility for reporting truthfully is non-zero. So it's better to participate than to not participate and like get nothing and pay nothing. Okay. So the main thing to remember here is that this does, for this instance, like for the finite instance where we just have like 2 different values for each of the items, you can solve this. Like this exactly solves the revenue maximization problem. You will get the solution that like optimizes the revenue truthfully. But even for the simple instance, this approach is exponential, right? This is like an exponential size LP because you have exponential many variables and constraints. Okay. So can we do better? The question is, can we find a polytime solution, right? Unfortunately, the answer is no. This is a computationally hard problem. And again, as like Ravi asked, like, do we get something better because of finite support? It turns out no. Shen et al. Have this nice result that shows that even when the support size of each of the items are just 3, okay? So each item takes at most 3 different values. We can't find the optimal mechanism in polynomial time unless the whole polynomial hierarchy collapses. Okay. So this is not just about the continuum, but like even when you only have finite support and like of just size 3, you can't find the optimal mechanism in polynomial time. Okay. But no worries. As I said, like we know how to handle hard problems, we approximate, right? So in a line of work started by Chawla et al., we know that you can find a 1/4 approximation to the optimal revenue in polynomial time. So there is this simple mechanism that gets 25% of the revenue. Okay, but is 25% of the revenue really good enough? Can we do better? Do we really want to sell something that's worth $1,000 for just $250? Can we do better than a 1/4 approximation? And until now, we didn't know anything better than a 1/4 approximation. We didn't even know a 1/4 plus epsilon approximation for this setting. And our work tackles this and answers affirmatively that yes, we can do better, and we can do much, much better. We can get a 1 minus epsilon approximation to the optimal revenue in quasi-polynomial time in N. Okay. So again, just to like recall quickly, even when the support size is just 3 for each of the marginals, Shen et al. Showed that the optimal is a computationally hard problem. Like finding the optimal mechanism is computationally hard. And Chawla et al. Showed that you can find a 1/4 approximation in polynomial time. And we extend this to say that we can get a 1 minus epsilon approximation, but in quasi-polynomial time, we get a QPTAS. Okay. And there is a very similar, oh, sorry, my bad. Yeah, okay. Yeah. So this, our result for the QPTAS is not just for like finite support marginals. We show that this holds even when the supports are like unbounded. So there is no restriction on the marginals or anything. So as long as we have a product distribution, that is the items are independent, in the unit demand setting, we can find like almost optimal revenue in quasi-polynomial time. Okay, and this is the first such like sub-exponential time approximation scheme like in this line of work for like such a like general class of distributions. Okay. Yeah, and a quick side note about like the additive bias setting. This also has a very, very similar history. Daskalakis et al. Showed that even when the support size is just 2 for each of the marginals, finding the optimal is computationally hard. And Babayev et al. Show that you can have a simple mechanism that gets 1/6 approximation in polynomial time. And we again extend this to a QPTAS. We get a 1 minus epsilon approximation in quasi-polynomial time. But this result holds only for any finite support marginals. Okay. And we also have like other interesting results in like different restricted settings. You can ask me more about like them later if you're interested. But yeah, coming back to our main result for the unit demand case, we show that we can find a 1 minus epsilon approximation to the optimal revenue in quasi-polynomial time. And this holds for any product distribution. There is no restrictions on the marginals here whatsoever. Okay, cool. So yeah, if there are no more questions about the result, like I can get into a little bit more detail. Okay. So I'm not going to be proving our results as such today. Instead I want to like talk about what are the technical challenges in like going beyond what was previously known in this setting. Okay, so I want to start by talking about a very special case of our setting called symmetric distributions. And this is the only case where we really knew something. Like beyond this, we really do not know anything before in this setting. Okay, so these special kinds of distribution, like this special case of our setting called symmetric distributions, was studied by Daskalakis and Weinberg. Don't worry about the text on the slide for now. So they showed that you can find the optimal mechanism in polynomial time for this very special kinds of distribution. Okay, so they have this nice result that completely solves this problem, but for this special kinds of distributions called symmetric distributions. Okay, so what do I mean by symmetric distributions? Let's like look at a toy instance to have some intuition. So like let's consider a buyer type from the distribution whose value for the soccer ball is 5 and her value for the basketball is 8, and consider a different buyer type with swapped values. Her value for the soccer ball is 8 and her value for the basketball is 5. Okay, so if the probability of drawing these two buyer types is the same from this distribution, and it is the same for any pairs of value x and y, we say that the distribution is symmetric about swapping the basketball and soccer ball. Okay, so for any x and y, if the probability of seeing xy is the same as the probability of seeing yx, we say that the distribution is symmetric about basketball and soccer ball. Oh yeah, there's a question.
So if you're working with independent distributions, that means you have to have uniform distributions, right?
So this one in some sense means that, yeah. So for example, this basically kind of says that like the things are identical. Yeah. So at least for soccer ball and like basketball, they're saying that like you have identical distributions. Correct. That's a good point. Good. I mean, good question. Yeah. Yeah. So exactly. So we say that a distribution is symmetric about swapping if the probability. I will tell you why I'm talking more in terms of like probabilities in a second. But yeah, this is a, you can think of it in both ways, whichever makes it more easy for you. Yeah, so we say a distribution is symmetric about swapping basketball and soccer ball if like the probability of seeing xy is the same as yx. Right. So in more generally, we say a distribution is symmetric with respect to a permutation sigma if the probability density of seeing v, so f of v, is the same as the probability density of the permuted type sigma v for all buyer types v. Okay. And why do we care about this? Like, why am I talking about like symmetric distributions? Because this reduces the problem size a lot by grouping together equivalent buyer types and treating them similarly. For instance, consider this very highly symmetric case of n IID items. All the items have identical distributions. Again, the items take value 1 or 2. So recall that we've already seen this distribution. We tried to solve this using a naive LP, and we know how that goes. So we have 2 to the n many different types of buyers, and the naive LP solves this exactly, but it does so in exponential time. Right? Even for the simple instance, this LP takes exponential time in n because there are exponential many variables and constraints. But here we note that to capture like the different buyer types in this distribution, all we need to know is how many items are valued at 1 and 2. So here to capture like different buyer types, all we need to know is like how many items they value at 1 and how many items they value at 2. So we have a representative RK for all buyer types with exactly k items with value 1 and n minus k items with value 2. Okay, so like we have like R0 through like Rn, right? And we see that this reduces the number of variables that we will be using from exponential to just linear, like to just like n variables or like order n variables. That is, we can have a similar LP like the naive LP, but here instead of having variables like for item allocations and price for all buyer types V, we only have it for the like n representatives R0 through Rn. Okay, and the objective is again to maximize revenue. So this is like one of the reasons why it's nicer, or like it's one way to look at symmetric distributions is through like having like the same probability of seeing, because now I can group together buyer types with the same representative and they all have the same probability of being drawn. And this exactly gives us like the revenue max, like the objective is to maximize this revenue. Okay, so we again have similar constraints. These are just like the constraints from before, and we have one more constraint which makes sure that like these representatives are actually representatives. Basically it makes sure that like what we are allocating to them makes sense in terms of like how their representatives will or like their representatives or like people who are represented by them will get from this. Anyway, the main thing to note here is that here now in polynomial time, you can solve the exact revenue maximization problem. Like this solves the original revenue maximization problem. I haven't like, I didn't lose anything by doing this trick. I can get the optimal revenue for the original revenue maximization problem for this instance, but I can do this in polynomial time. Okay, and this exactly is the spirit of the Daskalakis-Weinberg result in some sense. So they consider distributions where each item can be partitioned into S different groups, and within each groups, all the items are identical. They are just drawn IID. Okay, and the support size of each of the marginals is finite, is at most C. So they show that when for these kinds of distributions, you can find the optimal mechanism in time n to the CS. Okay, so we have S different groups of items, and within each group, all the items are identically drawn. And the support size is going to be small. It's going to be just C. So for these kinds of distributions, they show that you can find the optimal mechanism in n to the CS. And this is again just counting representatives. It's just like a balls and bins counting, because in each group there can be at most n items that take a particular value X, but we know that there are only like C different values X that in the support. So you can take, then there are S different groups. So the number of representatives you need to capture is just n to the CS. Okay, so this is just like a balls and bins counting, and we will do like the similar trick as the identical case, and you can get like the optimal mechanism in n to the CS time. So like the main thing to remember is that as long as you have finite support marginals and only few distinct kinds of marginals, you can find the optimal mechanism in polynomial time. Okay, but this is only for this very special case of distributions. This does not even capture all finite marginal support distributions, right? Like this is only for like these special kinds of distributions, and we do not know how to extend this to like cover all finite support distributions before. So for example, consider again an instance where items just take value 1 or 2, but like now it's a very asymmetric instance. All the items have like different marginals. Here we know that the naive LP will go through and we can solve this in exponential time. We can get the exact solution in exponential time. But can we do better? Like how can we can we get a polynomial time solution? We don't know. We don't even know whether or not a p-task is possible, like for like the bounded distributions or like finite distributions. We still don't know whether a p-task is possible actually. Okay. So yeah, so the main takeaway from this part is that symmetric distributions are great. We can find the optimal mechanism for them in polynomial time as long as you have small marginal support and only a few distinct kinds of marginals. But this is only for the special kinds of distribution. We don't know anything beyond this. We don't know how to extend this to like finite support marginals or like bounded product distributions. Okay. So next, I want to talk about the challenges in why it's so hard to go beyond symmetric distributions to like finite or bounded distributions. So you might think that why can't we do some sort of a transformation to go from any like bounded distribution to like symmetrize it to like a close symmetric distribution and then use the previous results or something. The challenge here is that it is very important like what we mean by close, because just because two distributions are close in some sense does not mean that their revenue is going to be preserved. Like for example, consider this distribution D where the item takes value 100 with probability half and 0 otherwise. And consider this like quite a close distribution D prime where the item takes value 99 with probability half and 0 otherwise. So here, the optimal mechanism for D just sells the item at price 100, right? Like if you set price 100 with probability half, you sell and you get revenue 50, and this is optimal for this distribution. But the same mechanism is going to get 0 revenue for D prime. So we need to be extremely careful to make sure that the revenue is actually preserved in like closed distributions. And so for that, it is really important that we have the right metric of like closeness. Okay. But once we have that, then we show that you can just use the Desclarques-Weinberg result that we saw earlier to get the optimal mechanism for this closed symmetric distribution. And then to preserve the revenue, we do another careful transformation to go from this mechanism to a closed mechanism so that the revenue is preserved. So we do a careful transformation from like the distribution to the closed symmetric distribution. And then we do a careful transformation again from this opt mechanism for the symmetric distribution to the mechanism that we are actually going to use for the original bounded distribution. And we show that this preserves the revenue and we can get almost optimal revenue in quasi-polynomial time. And that's exactly what we do. So like I just want to like mention again that like just because two distributions are close does not mean that like the revenue is going to be preserved, and that exactly is the challenge. But once we have the right definition of closeness and we make sure that like we find the right mechanism to preserve the revenue, we show that we can get almost optimal revenue in quasi-polynomial time. Okay. So the like main takeaway from this part is that symmetric distributions are like extremely fragile. We need to like really handle them with care, because we can't say that, oh, something is like almost symmetric, so like, oh, it's easy, we just get almost optimal mechanism. Like we need to make sure that like we can do a careful transformation to actually preserve the revenue. And we do that. We do this for all bounded distributions. We show that you can do a careful transformation to a closed symmetric distribution to preserve revenue. Okay. So next I want to talk about the challenges in going to all the way to our general setting of unbounded distributions. So here, the main challenge is that if we want a 1 minus epsilon approximation, then we can't just fully ignore high valued bias. Why can't we, like the reason why we can't just chop off the tail at some point, because the probability of seeing values greater than some number is so low that we can't just chop them off, because if we want to get 1 minus epsilon approximations, we can't just ignore the high value like buyers. For instance, consider this example where we have n identical items with a very high probability. The value for the item is drawn from uniform 0, 1. And with a very small probability of 1 over n square, it takes a huge value h. Okay. So now if we only focus on the core, that is we ignore all these tail values and only focus on the bounded interval 0, 1, we can get revenue almost close to 1, because the max of like n uniform 0, 1 variables is going to be like very close to 1 with high probability. So if you set that price, it will sell with a very high probability and you can get revenue close to 1. Okay. But instead, if we focus only on the tail or like only on this like high value buyers, then you can price all the items at like price h, and with probability 1 over n, at least one of them is going to take value h. So we can get revenue h over n. Okay. So now if these two revenues are comparable, that is h is like order n, then we can't just ignore one or the other. We can't just ignore the trail. Actually, we can't just ignore the core either. Like we can't ignore one or the other to get better than a constant approximation. Like if we ignore one, we can't do better than a constant approximation, and we are interested in 1 minus epsilon approximations. So we have to handle both, and that is like the tricky part. And I'm going to call such distributions almost bounded distributions. Okay, I'm going to call distributions where the marginals are basically just a bounded interval, except for one high value h. Okay, so the support is just the union of a bounded interval and a singleton high value h. And we show that we can actually get a polytime reduction from solving for unbounded distributions to get 1 minus epsilon approximations for unbounded distributions to just solving for almost bounded distributions. That is, it's enough to just find additive epsilon approximations for almost bounded distributions. So we can't just ignore the high values, but we are showing that we can just capture the tail with just one high number, and that's enough. Okay. So again, we have a black box reduction from solving for unbounded distributions, finding 1 minus epsilon approximations for unbounded distributions, to just finding additive epsilon approximations for almost bounded distributions. And such a reduction was kind of shown before by Babayev et al. For the additive wire setting, but they show an almost reduction to a truly bounded distribution. But as I said, there is this fundamental challenge in like fully like reducing it to a true bounded distribution. That's why they get an almost reduction, and we get a true black box reduction, but to almost bounded distributions. Okay, and our results holds for like even for more general class of valuation functions like subadditive bias. So we believe that this is going to be very crucial in extending our results beyond the unit demand case, because now we only need to focus on almost bounded distributions. Okay, so the main takeaway from this part is that we have a true black box reduction from unbounded distributions to almost bounded distributions, like in polynomial time. We can't just ignore the high values completely, but we can just capture the whole tail with like one single number h. Okay. So also like recall that I said that like we can symmetrize any bounded distributions to get like to preserve revenue and get almost optimal revenue. But it turns out that like our result actually holds for like any almost bounded distributions. So we can do a careful symmetrization of any almost bounded distribution to preserve the revenue and get almost optimal revenue in quasi-polynomial time. So putting these two things together, we get our main result. So in the unit demand setting, like as long as the items are from a product distribution, we can get a 1 minus epsilon approximation to the optimal revenue in quasi-polynomial time in n. Okay, and we do this in two key steps. One is the polytime reduction from unbounded distributions to almost bounded distribution. And 2 is a careful symmetrization of any almost bounded distribution to a closed symmetric distribution, and preserving the revenue to get almost optimal revenue. Okay. Do you have like any questions about this part?
So maybe I can ask one question. How should I be thinking about this symmetrizing? If you solve the exponential LP, right, which you're originally trying to solve,
yeah,
and you think of symmetric solutions as one which have positive mass only in certain spread out ways in that exponential.
exactly.
So you try to find something like that. So you impose the solution to the closest ssolution of that.
Yeah. Type. Yeah, good question. So yeah, let me just clarify it once more. So I didn't fully explain what I meant, but like that's exactly what we're doing. So in general, an optimal solution, let's say, has some LP, like let's say it has some mass and like different allocation price probabilities, but like we are trying to find a solution where the options are just like permutations of each other, right? Like if RK is my representative, then my true value, I'm going to find solutions where my allocation is literally a permutation of RK, like how they represent me. Exactly. So we are kind of restricting ourselves to solutions that have this structure. And the nice thing is that, of course, this makes sense for symmetric distribution, right? Okay, of course, in hindsight, that's like Daskalakis Weinberg results. Like it makes sense for symmetric distributions to have symmetric solutions, and they show that like it is optimal. And we are just like trying to like, and this is all like was done using their results. Like nobody like tried to like use their symmetric solutions somewhere else. And what we do is to say that forget like whether or not my actual distribution is fully symmetric. It's probably not. Like I can have like n different marginals and like it's a very highly asymmetric instance, but it does not matter. I'm going to find something that is still a symmetric solution, which is going to preserve revenue and give me like almost optimal revenue. Like even though I am a very asymmetric distribution, like my distribution is very asymmetric, I can still find this like very symmetric solution by just restricting myself to this symmetric space, and that still works for me.
So is it some sort of rounding result where you have values on all these exponential points?
Nice, yeah.
You have your probabilities in the lottery, in the mechanism, and then you know that the set of probabilities you're allowed are those resulting from symmetric distributions, and then you have values and you have to kind of round it.
So not quite. It's not actually like, okay, it is a little bit like that. It is kind of like a rounding scheme, but I think the more intuitive way to think about it is to say that let's say my distribution is very highly symmetric. What I'm actually going to do is round my probabilities down, where like, so first of all, my support is just going to be restricted to like, let's say only epsilon 2, epsilon 3, epsilon through 1. And my probabilities are also going to be rounded to the nearest thing. So basically I'm saying that take any asymmetric distribution, I can now map it to one of these kinds of distributions where the supports are all like multiples of epsilon, and the probabilities are like kind of like powers of 1 minus epsilon. Like this is literally what we do.
I see. So you do it in the input space itself.
Exactly. We are doing it in the input space, but like we are showing that that makes sense to do. Like, of course, this is not done yet. We need to show that like we do the rounding in the input space, and we still do a little bit of a rounding in the output space too. That is the closed mechanism that I was talking about before. So we do a rounding in the output space, but most of the rounding comes from the input space, and we show that like we can still preserve revenue by doing a simple rounding in the output space, and everything carries over.
Yeah, thank you.
Yeah. Good question. Thank you. So yeah, in the last few minutes, I want to like quickly change gears and talk about a different lens of simplicity called menu complexity. So a menu is just a collection of all possible distinct outcomes of a mechanism. Okay, so it's just the collection of all possible allocation and price output by the mechanism. So this is one possible menu. But we could also have like randomized allocations and price as well. Okay, so it turns out a menu is equivalent to a truthful mechanism. That is, if I give you the list of all possible options and ask the buyer to like choose from it, it's equivalent to running the truthful mechanism and like outputting like the corresponding allocation price for this particular buyer. And this is just because of like incentive compatibility or truthfulness, right? Because the buyer type does not want to lie about their value. They will report truthfully. So it's the same as saying that like they prefer their allocation and price over any other allocation and price. So if you list everything, they will go take their corresponding allocation price. Like the main thing to remember is just like a menu is like equivalent to like truthful mechanisms. And the menu complexity of a mechanism is just the number of distinct outcomes of the mechanism. So like the size of this equivalent menu that I'm like showing the buyers. Okay. Yeah. And we define a new notion of symmetric menu where we give a more compact menu while implicitly agreeing to something. So here, instead of like listing out all of these 7 different options, it's equivalent to like just give this smaller menu where I say that take any one ball, pay $6, take any 2 different balls, pay $10, or like take all 3 balls and pay $14. And the asterisk here basically says that you can take any combinations of the balls without explicitly listing all the different combinations. Okay, so like we are just getting a more compact menu while like implicitly agreeing to something. And so in a symmetric menu, we are along with the options, the allocation and price, we are also given a permutation group sigma. So when we are offering an allocation A at price P, we are also implicitly giving the options of the permuted allocations at the same price P. Okay, so that is the symmetric menu. And it turns out symmetric menu complexity, which just counts the number of options in this compact menu, is a proper generalization of menu complexity. Because if we just take the trivial subgroup of like just identity permutation, then menu complexity and symmetric menu complexity are exactly the same. But in general, we can get a more compact menu while implicitly offering all corresponding like relevant permutations. Okay. So for example, consider this mechanism where it allocates exactly one item at price 1. Okay, so the menu complexity of this mechanism is actually n, because you have to list out the options: take item 1, pay price 1, take item 2, pay price 1, and so on, like take item n and pay price 1. So we have like these n different options, but the symmetric menu complexity of this mechanism is just 1, because equivalently I could have said take item 1, pay price 1, or take any permutation of this allocation, that is take any other item and pay price 1. Okay. Here is another example where the mechanism outputs all possible subsets of items, and the price of each subset is just the size of the subset, like the number of items in the subset. So again, here the menu complexity is actually exponential, but the symmetric menu complexity is like linear, because instead of listing out all the 2 to the n many different possible subsets, all you have to do is to have one option for each size. So I can just have one option for each size and like allow all the permutations, which will capture all the different subsets at the same price. right? So the menu complexity here is 2 to the n, but the symmetric menu complexity is just n.
So you don't include the complexity of the permutation?
So, okay, good question. So like one way to, okay. So since we like restrict ourselves to like permutation subgroups, the computational complexity. So for example, menu complexity is a nice way to like think about communication complexity. My bad. I meant communication complexity, because like if you have all of these options, take a log of that, and that's my communication complexity. But now when I'm like also giving my permutation subgroup, there is like all these nice results that show that like any permutation subgroup just needs like log n, like n log n communication complexity.
Oh, nice. Okay.
Yeah. So which makes it very nice. So like I like, sure, there are some permutations that are like easier to like, it's more simple. Like saying that you can take any permutation is actually such a simple mechanism. But like even complicated subgroups, you can the communication complexity of telling it is just like n log n. Yeah. So the second part of our main result like studies like the trade-offs of simplicity and optimality for this notion of like symmetric menu complexity, and we show that the same almost optimal mechanism that we saw in the first part has only like quasi-polynomial symmetric menu complexity in the unit demand setting for any product distributions. So you can get almost optimal revenue from a menu with like almost polynomial symmetric menu complexity. Okay, so like that also, as I said, means that like you have like all like basically like logarithmic you also have like almost efficient communication complexity because of this, right? Yeah. So we also have like other results like analogous to the computational setting in some sense for like different restricted settings. You can ask me more about them later if you're interested. Like we have like analogous results to like symmetric menu complexity as in like computational complexity. Cool. So with that, I think I'll wrap up with a summary. So we saw that optimal auctions can be like in the multi-item setting can be very complex and like computationally hard. And our work gives the first sub-exponential approximation scheme, like the first sub-exponential mechanism that gets almost optimal revenue for a very general class of distributions called like in the unit demand setting. We also give a true black box reduction, like a polytime reduction from solving for unbounded distributions to almost bounded distributions. And this holds even for like more general valuations like subadditive bias. So going forward, we only need to focus on like almost bounded distributions. We also exploit symmetries in seemingly very asymmetric distributions by doing this careful transformation and like preserving revenue. We introduce a new notion of symmetric menu complexity, and we have like interesting results here as well. So yeah, there are many open questions in this line of work. For example, can we again extend our results beyond the unit demand case? Like for the additive setting or even for subadditive bias, can we get like sub-exponential time approximation schemes? And and as I said earlier, like we don't know whether or not a p-TAS is possible like for the unit demand case, even when we have like bounded or like finite distributions. So can we improve our upper bounds like to like polynomial time approximation schemes, or like can we prove like better, like stronger lower bounds? Also like note that in this whole talk, I've only talked about like the single buyer setting, but the multiple buyer setting is also like very interesting and it's been very well studied. So like, can we generalize our results to like the multiple buyer setting in some way? So yeah, with that, I think I'm going to end here. Thank you for listening. Let me know if you have any more questions.
Thanks for the talk. There's some nice work by Francois Margot on symmetries in integer linear programming.
Ah, okay. Sorry, can you repeat the name again?
I'll send you a link. Yeah.
Okay, yeah.
And
Oh,
so
nice.
there might be some, he might already have thought about, but of course he was trying to reduce the complexity of branching, because
I
you
see.
don't want to keep branching on the same thing which has been on before.
I see.
But
Interesting.
he may have some ideas about the right subgroups and so on.
Nice. I see. Okay. Yeah, that sounds interesting.
I'll send you a link.
Yeah. Thank you.
Yeah. Thanks for a nice talk.
Thank you.
I have one question.
Mhm.
So how efficient is it to actually run the mechanism? Because you said you can get the mechanism in quasi-polynomial form.
Yeah.
Run.
So I don't think Google should be running our mechanism to run like add options, for example. So yeah, so quasi-polynomial is not, so I feel like technically it's like better in some ways than like a polynomial thing where, you know, like n to the 1000 is going to be bad. Maybe quasi-polynomial is like better than that, but like nobody runs an n to the 1000 like polynomial mechanism either. So I would say I have not tried running the algorithm, but like I think.
No. So sorry. So to find the optimal mechanism, you said it's quasi-polynomial.
Okay, I see. Okay,
Yeah.
you're not asking like let's apply this to a real life setting. Okay, yeah, it is going to be quasi-polynomial to run it either. So the finding is quasi-polynomial and running it is also quasi-polynomial.
Oh.
Yeah, because like basically you will run the LP in some sense, and the LP is going to be quasi-polynomial.
Okay.
Yeah, good.
I posted a link that you can click through.
Oh, nice. Thank you.
I have a question. Sorry. So you say the LP will also be quasi-polynomial. So that's because you still like, so the number of variables is still that size. Is that the reason?
Yeah. Basically, that's what's going to happen. So then, so basically, as I was saying, what we do is to find a closed symmetric distribution and like solve it, right? And then so it turns out the closed symmetric distribution, the C or the S. So what does the symmetric distribution result says? If you have marginal suppose C and like few distinct kinds of marginal like number of S, like S, the time is like n to the CS. So it like what we don't go all the way and show that it like both S and C are constants.
Basically, on the log test.
Yeah, so like there is going to be a log factor there, and that's kind of like, so it's not clear that whether we need it. So it would be great like if we can like make it into like a polytime approximation scheme, but like the rounding becomes basically the way we round it, the error is too much if we make it a constant. Like we need the log n, like it kind of is a balancing act to get 1 minus epsilon approximations. Like it's not too coarse that like you're not close enough, but it's all we also need it to be just fine enough so that like
so you still get the right cover all the ranges. I see.
Yeah. So if you're actually interested in this kinds of stuff, like for the additive setting, the reason why, like, for example, our results don't carry over immediately is that we are not able to like even do better than like n in the exponent. Like if you like to get a 1 minus epsilon approximation, like with using these kinds of machineries and stuff, the symmetry stuff won't help much because you need like you need the closeness to be so fine that like the exponent will still have like an n there, so it becomes like exponential. It becomes like n to the n, which is,
I see.
Yeah.
Oh, it's pretty cool. Oh. Thanks.
Yeah, if there aren't any more questions for the speaker, let's thank the speaker for a great talk and end the session.
Thank you.
Thank you.
Thank you.